Hello, welcome to the video. In this lesson, we're looking at section 5.7, where we're going to take a look at systems of linear inequalities. So early on in the chapter, we looked at systems of linear equations. What that meant was anytime you had two unknowns, you needed two equations in order to discover what those values for x and y were, where the intersected line was, or if they just so happened to be parallel was no solution. If it was the same line and ended up being infinitely many. Linear inequalities are solved by graphing, and you're still doing that shading like we did in 5.6, but there's going to be a more detailed shading which is going to satisfy both inequalities. For starters, what we're going to do is just like what we did with the systems of linear equations, we're going to look at a singular ordered pair to see if it is in fact a solution or not. All right, just like with the system, as long as it satisfies both equations like it did early on in the chapter, the same idea is what will work in this section. It has to satisfy both inequalities in order for it to be a solution. So I have, for part A, I have 3 comma 5. So I have to see if it works in the first inequality. Remember that 3 is x and 5 is y. So for the first one, it is going to look like 5 is less than 2 times 3. Well, what is 2 times 3? 2 times 3 is 6. So is 5 less than 6? Is that true? The answer is yes, this is true. Is that a solution? Well, we're halfway there. We have to see if it now works for the second one. So now for the second one here, I have 5 is going to be greater than or equal to x, which is 3, plus 1 is 5 greater than or equal to 3 plus 1, which is 4. Is this true? The answer is yes. So since 3 comma 5 satisfies and makes a true statement to both inequalities, 3 comma 5 would in fact be a solution. When you look at the second example, -2, 0, again, this is x, this is y. If you look at the first inequality, is 0 less than 2 times -2, which means is 0 less than -4? No, this is false. I don't even need to check the second one. As long as I have one false statement, this is an indicator that this is not a solution to this system. It may very well have been a solution to inequality number 2, but that doesn't matter. It has to satisfy both of them. So this is what I was talking about. If you look at the graph, this is what I was talking about with respect to having a final shading. So if you notice, there is um, some color shading in this particular one. There's a blue, there's a red, and it looks like there's a purple. I believe that's what blue and red make, is purple when you mix them together. Ask your art teacher, please. But anyway, what we're looking at is this. Everything that is blue is what, and also purple, is what satisfies the inequality y is less than x plus 2. So everything that was blue and purple satisfies that. Everything that is red and purple satisfies the inequality y is greater than or equal to 2x minus 1. Now, The thing that we have to keep in mind is there is going to be I call it a final shading. And this is the one that is the most important one. And the most important shading that we're looking at is the one that shades both the blue and the red. The purple one is what we're really looking for, because what that one is, that final shading, is those are all of the points that would satisfy both of those inequalities. Those points are what are going to satisfy that particular system. And that's really what we're looking for. We're looking for that final shading, all right? It's nice that we can have that we have an indicator of what is red, we have an indicator of what is blue, but in reality, we're trying to find the overlap. We want to find that overlap. So here, they want us to graph this linear inequality. So for starters, I have y is less than or equal to 3. It's a horizontal line at 3, and because it's equal to, it's a solid line. So we're still looking at solid lines and dashed lines in this particular instance. And what you're going to do is you're still going to use a test point. So I'm going to say, oh, this is my test point, 0, 0. And is 0 less than or equal to 3? Is that true? The answer is yes, this is true. So what I would advise you to do is just have an idea, and I would just kind of put an X on the bottom, where if this was the only inequality that we're using, that's where the shading would go. But we're not dealing with just one inequality. We have another one to look at. So looking at this one, y is greater than x plus 2, it is in slope-intercept form, where my y-intercept is at 2, so it's at 0, 2. And my slope is 1, so it's up 1 to the right 1. And this one is going to be a dashed line. And I can still use 0, 0 here. And is 0 greater than 0 plus 2? Is 0 greater than 2? Is that true? No, that's false. So that means that everything is going to kind of go away from the test point, which is over here. So I kind of put that X on that side because this is kind of an indicator. So I'm just going to use black as my final shading. My final shading is going to be this overlap right here. This triangle on the graph is what satisfies both inequality 1 and inequality 2. Because it should be below the boundary line on the horizontal line, and it's going to be on the left side of my diagonal dash line from inequality 2. Same idea. We're looking at what I would do is create both inequalities in slope-intercept form. So for inequality 1, it's going to turn into some subtract 2x, so it's going to be y is going to be less than negative 2x minus 1. And for inequality 2, it's going to be y is greater than negative 2x plus 3. So I don't know if you noticed this, but they have the same slope, which means that those lines are going to be parallel. So here is how we go about solving that one. I have negative 1 as my y-intercept. It looks like it's going to go down 2 to the right 1, to right 1. Or I can go up to the left 1. And it's a dashed line. All right, I can use a test point of 0, 0. And looking at this, is 0 going to be less than Negative 2 times it by 0 minus 1, which means is 0 going to be less than negative 1? Is that false? Yes, that's false. So this is a false statement. So that means that my shading is going away from the test point, which is on the left side. So I just put a little X there. Looking at the second inequality, 0, 3 is my y-intercept, and my slope is still negative 2. So it's either up to the left one or down to the right one. Whatever you are thinking. And this one is also a dashed line as well. So in this particular one, I could still use 0, 0 as my test point. And I have 0 is greater than negative 2 times it by 0 plus 3. Is 0 greater than 3? No, that's false. So over here, this is going away from my test point. Now this is unique, so if you notice, for my first inequality, the one in green, the shading is going to go here. For my second one, the shading is going to go here. Now, what do we notice? We do not notice an overlap. There is no overlap. Since there is no overlap, this is an example of a system of linear inequality that has no solution. There is no solution for an ordered pair of x comma y that would satisfy both inequalities. All right, for the last couple of examples here, we are going to be given a graph and we are going to be asked to solve the linear system. So let's just say that, let's say like this dash one here is number 1. We'll say this one here is number 2. So looking at number 1 here, in slope-intercept form, it looks like I have a y-intercept at 0. So it's going to be y. I'm not putting greater than, less than, greater than, or equal to, less than, or equal to. I'm not putting anything like that. My slope is 1, so it's going to be x plus 0. So I'm just going to leave it as y is, it's either going to be greater than or less than because it's a dashed line. Since it's a dashed line, what I'm going to do here is I'm going to look at this portion right here where it's a true statement. And it looks like this is at 1, negative 1. So if I put negative 1 in for y and 1 in for x, what would my inequality have to be? It would have to look like this. So for my first inequality, it's going to be y is less than x. For my second one, it's a horizontal line, so I know that it's going to be y is going to be, this one's going to be greater than or equal to or less than or equal to, and it's going to be negative 2 because it goes along negative 2 here. And I know that it is above, so a true statement would be something like this. This looks like 0, negative 1. So if I put negative 1 in for y, this is negative 2, so that means that my inequality comes here, so y, and it's going to be greater than or equal to, sorry, because it's a solid line. So my system is going to be y is less than x, and y is greater than or equal to negative 2. So that comes from this portion of the inequality, this comes from this portion of the inequality, and I was able to figure it out from the final shading that holds true for both inequalities. Looking at one more, again, we'll call this inequality 1, we'll call this inequality 2. So looking at the first one, it's a vertical line. So now I'm dealing with x is going to be, in this case, because it's a solid line, it's either going to be greater than or equal to or less than or equal to. And it hits at 3, so it's going to be, so I'm just going to pick right here. And this is at 0, comma 2, so it's going to be 0 and 3 has to be less than or equal to, so less than or equal to 3 is my first one. For my second one, looks like my y-intercept is at -1, so looking at number 2 here, I got y, and looks like my slope is up 1, 2, to the right 1, 2, 3, so 2/3 x minus 1. And the final thing is I got to pick a shading. So actually I can pick 0, 0 as my test point. So I can say, oh, 0 and 2/3 times 0 is 0. So I have -1. This would be greater than, and it is greater than because this is a dashed line. This was a solid line. That's how we had the equal to indicator. So now y is going to be greater than 2/3 x minus 1. So to finish up, x is going to be less than or equal to 3, and y is going to be greater than positive 2/3 x minus 1. Those are the inequalities that would satisfy that particular system. And that is being able to solve systems of linear inequalities. Hope this helps. Until next time.